at the beginning. Okay, so in a rolling projectile, what type of velocity did it start with? Horizontal or vertical? Horizontal. It started with horizontal velocity, right? Because the incident left the table or left the cliff or whatever it was only moving horizontally. Now we're leaving with both horizontal and vertical velocity, right? It's going to go up at an angle and then come back down. Okay, that's really, really, really important. So now in our projectile equations, Vyi, right, initial vertical velocity is not going to be 0. Okay, so we're going to have much more of those components. Okay, so if I punt a football into the air at an angle of 40 degrees with an initial velocity of 4.2 meters per second, what are the components of that vector? Okay, so this is not even into projectiles yet. This is just looking at breaking down that initial velocity vector, and we know how to do that. Okay, so I want to see if you can draw this vector correctly. If we were just given 40 degrees, right, where do we think that 40 degrees is probably going to be? Yeah, from the horizontal, right? So here's my starting point, okay? And so that means it's going to go like this. It's going to go up into the air at 40 degrees. It's going to go up, reach its peak height, and then it's going to come back down to the ground, right? So here might be its peak height right up there. Okay, but all we're looking at right now is this little portion of the motion, okay, the starting point. It's leaving my foot with an angle of 40 degrees at a velocity of 4.2 meters per second. So 40 degrees sits right here. And where would the 4.2 go? On which side? Right here? There? Yeah, the hypotenuse. That's right. Yeah. That's our total velocity is 4.2 meters per second. So we need to break that down into what's the vertical velocity and what's the horizontal velocity. Okay? So how do we go about doing that? Right? If we have our hypotenuse and we have an angle, we're going to use our trig functions, right? We know how to break down vectors. So if this I know is my initial velocity, what would I call this side right here? Vyi, right? It's initial velocity, but only in the vertical direction. And so this side I would call Vxi. Okay? Do those variables, can they be found in your projectile equations? Yes. The answer is yes. Okay? So we took this initial velocity. We're breaking it into initial vertical and initial horizontal. We're going to be able to use those numbers in our projectile equation. Okay? So let's go ahead and break this vector down. Okay, to solve for Vyi, you're using sine or cosine? Sine, good. So 4.2 sine of 40 degrees. Make sure that you are in degrees, not radians. And I got about 2.7 meters per second. Yeah? Okay, good. And then for Vxi, we're going to use cosine. Good. So 4.2 cosine of 40, and that gives us 3.2, 3.22 or 3.21, okay? Wherever you want to round that is fine. Okay, so here's the really important part. Now, this would be just the beginning of our projectile problem, right? This would be the first step. And once we've done that step, we're done with 4.2, we're done with the 40 degrees. 4.2 would never go into our problem, right? We're only using vertical and only using horizontal. This one that's at an angle, we don't use that anymore, okay? So we would be able to plug these numbers into our equation for Vyi and Vxi. Does that make sense? Okay, so that's the only difference between rolling projectiles and launch projectiles is that we start now with some new information, which means our equations become a little bit more complex because we can't just drop the 0 in that one equation, okay? Okay, we're looking at the same type of start. Now we're going to go and complete the whole projectile path. Okay, so go ahead and get written down here what you need to, and then we'll work through this together. Okay, so first thing we want to do is draw our diagram. Diagram can be very simplistic here, but we want to draw a diagram. So we want to draw where we're starting our motion. So where is the motion going to start from? the ground, right? Not on a cliff, not on the ground. Or we're starting from, we're assuming that we're kicking the ball off the ground. Okay, it would tell us if we were kicking from a height of 1 meter or whatever. That would change our problem a little bit. But here we're starting from the ground. Okay, so I'm going to put my origin where the motion starts from. I know my projectile is going to go up at an angle. It's going to travel through the air. Then it's going to come back down. Okay, you don't even need necessarily this whole trail, this trajectory of your projectile to be drawn, but you can if you want. It's not that huge of a deal. What we're really focusing on is this beginning part. Okay, so it was kicked at an angle of 37 degrees with a velocity of, 20 meters per second. That's pretty far, or pretty fast. Okay, so this ball is going to go pretty far. All right, let's break down that initial velocity vector first. Okay, so this side of our initial velocity vector would be called what? What would we label this side? VYI, good. And that's one of our projectile variables. This side would be VXI because it's the initial horizontal velocity. Okay, so as we start to make our lists and our margins, we can use those. VYI, we're going to take 20 times sine of 37, and we get about 12 meters per second, right? Do we agree? Okay, and then for VXI, what do we get? 16, good. Okay, so now we're done with the 20 meters per second. We won't ever use that part again. Okay, so if it helps you to cross that out or to eliminate that from your list, that's fine. All right. We want to find the maximum height and the time of travel before the ball hits the ground again. Okay, maximum height. What variable does that mean we're solving for? What'd you say? Yeah, y, good. Right, we're solving for y. We use x and y as our distance now. So since we're solving for the height, we're going to use the, oh my, you can't even see that on your screen. Okay, so y and x are our distances now. So since we're solving for our vertical distance, we're going to solve for y. So I'll put my question mark there. Okay, what do we know about y initial and x initial? They're 0 because we chose our origin at the beginning of the motion. So our initial positions are both 0. These guys you don't even have to necessarily put in your list, but if it helps you to see those variables listed as 0, do it. Okay. What else do we know about something at peak height? What do we know about its vertical velocity at peak height? It's also 0. So that means Vy final is 0. Okay? And this one you might want a little star by because we know it's only at peak height. Okay? Vy final is 0 and it's only at peak height. That's not 0 when it goes up and comes back down, right? We're just looking at peak height right now. Okay? So let's start looking at our equations. Do we see an equation we can use to solve for the maximum height? Look through your projectile equations. Probably want to look through the vertical ones. The second one? Do we have time? We don't have time. Okay? So that would leave us with the third one, right? And the third one looks like this. VYF squared equals VYI squared plus 2AY minus Y final minus Y initial. What do we know about acceleration in the vertical direction? Good. It's always negative 9.8, always gravity. Okay, so this is at peak height. This is really important. Okay, Vy final is 0, so 0 squared is still 0. Vy initial, we solved to be 12. So we're going to say 12 squared plus 2 times negative 9.8 times y final, right? And this is minus 0, so we can leave that off. Okay, so go ahead and do that algebra to solve for y final here. We would then subtract over 144. Please make sure that you don't just add over the 19.6. What should we be doing here?
Divide by.
We should divide by negative 19.6. Okay, are we agreeing there with our peak height? 7.35? Okay. Okay. Now the second, sorry, are there any people that have questions about how we got to that point? Okay, the second part asks us to solve for the time it takes before it hits the ground again. So does that mean we're solving for time to peak height, or we're solving for total time? Total time. Okay. Now there's two ways to do this. Do you remember when we did original kinematics that you could do a shortcut method, right, which means solve to peak height and then multiply by 2? We can do that here as well. The only time we can do that shortcut method is when the path of the projectile is completely symmetric. Okay, so here it's going to go up and it's going to land at the same height. So that's symmetric. That's going to work fine. If I had, let's say kicked something off of a cliff and it's going to go up and come back down, that's not symmetric. So we can't use the shortcut method there because the beginning to peak height isn't the same as the from peak height to back to the ground. Does that make sense? So it has to be symmetric. So in this case we can do the shortcut or we can do the regular method. I will show you both so that we know how to do both. Okay? So let's start with the short method first. Okay? That means the shortcut method means we're solving for the time it takes to reach peak height, and then we're just going to multiply it by 2 because it's going to take the same amount of time to go up as it does to come down. Okay? So let me clear this off here. Do we have any questions about this first part? We good? Can I get rid of that? Okay. So let's solve for time to peak height. What equation could be used to solve for the time it takes to reach peak height? Probably an easy one, right? The first vertical equation, right? Velocity y final equals Vy initial plus At. Right? Because at peak height, we know Vyf is 0. We solved Vyi to equal 12. Acceleration is negative 9.8, and we're solving for time. Okay, so we get t equal to 1.22 seconds. Is that our final answer?
No.
No, we had to double it because this is only the time it takes to get to its peak height. So we have to multiply it by 2, which gives us 2.44 seconds. Okay, that is our final answer, 2.44 seconds. Okay, pretty easy, right? The second way that we have to solve for time, if it's not symmetric, or if you can't remember the shortcut method, takes a little bit more work and it requires us to use the quadratic formula. Okay, so let's walk through that method one time. Okay, and you will have to use this method, so please don't, not do it. Okay, so 2.44 seconds is what we got when we found the shortcut method. Now let's try something else. Okay, can't use the shortcut method. Let's say we don't know anything else that we could do to solve for time. Now look through your equations and find out which one we would have to use, right? We don't know the final velocity as it's hitting the ground again, so we can't use that, right? Final velocity is not 0 when it's coming back down. So we can't use either of those equations. What does that leave us with? The second one, okay, which says y final equals y initial, Vyi t plus 1/2 at squared. Okay, so I do want you to walk through this so that you can refresh yourself on the quadratic formula when you have to use this method. Okay. Where is the object hitting the ground, or at what height is it hitting when it hits its final destination?
7.34.
That's when it's at its highest point, but when it comes back down and finishes its motion, where is it at? It's at the ground again, right? It's at the origin again. So y final is 0, y initial is also 0. Okay, it's starting and it's ending at the same height, which means that's going to be 0. Okay, vy initial was 12 times t plus 1/2 negative 9.8 t squared. Okay, so when we set up the quadratic formula, we need to get them in order of, I don't even know the word for that, your terms, right? Your squared term has to go first, then your regular variable, then the no variable, right? In the quadratic formula, is that ringing a bell? Hopefully. Okay, all that has to be set equal to 0. So we need to rearrange these terms a little bit if you can't see which one is A, B, and C. Okay, if you can, great. If not, we're going to rearrange them. So that would mean 0 equals negative 4.9 t squared plus 12t plus 0. All I did was rearrange these three terms, okay, to get them set up to match the quadratic formula, which means our A term is what? Negative 4.9 is A, 12 is the B term, and 0 is the C term. Okay? Do you remember the quadratic formula? No. Okay. Negative b plus or minus the square root of b squared minus 4ac all over 2a. It's really important that it's all over 2a. Okay, not just the square root portion. Okay, so let's go ahead and work out that quadratic formula. Alright, I want you to try this one on your own. This is extremely similar, if not exactly the same as the problem we just did. Okay? But you're going to try and do it on your own. Okay, this one we're solving for the same two things that we did originally. But we're going to go one more step and say how far will it travel horizontally as well. Okay, so now we're going to solve for three different things. The first step, however, is always the same. Okay, so get written down what you need to, and we'll start breaking down that vector. Okay, this side would be VYI, VXI. I think you should be able to do this problem pretty much on your own. Okay, but I'm going to keep working it up on the board so you can follow along if you get stuck. What does this tell us here? It's on level ground. What does that give us a clue as to? Starts at 0, right? And it's probably going to end at 0. It doesn't tell us it's landing below where it started. It's not landing up higher than it started. So that means that our y final and our y initial would both be 0. Okay, how long will it be in the air? That means we're solving for time. Okay, so to solve for time, I'm going to go ahead and use the shortcut method because it's symmetric. It's going to start and end at the same height. Okay, so to do that, I'm going to take Vy final equals Vy initial plus AT, right, our easy equation. First of all, do everyone's initial velocity components match mine? 3.44 and 5.51. Okay. Give or take a decimal for rounding. Yeah? Okay, if you have any questions as I'm working through this, please raise your hand and ask them. Okay, otherwise it seems like everybody's moving along at the right pace. Okay, how high will it go? What variable does that mean we'll be solving for? Y, okay? And this is y final at peak height, right? This is y final after the total motion. This one is right here. But this question asks us for y final at peak height, so we're going to use that a little bit different. Okay? What suggestions do we have for equations to solve for y final? What do we think? I'd probably go with the third one. We could do the second one, right? Because we know the time it takes to reach peak height. But the third one would work fine, okay? Because it's 0 squared equals 3.44 squared. Is that what you had? 0.604 or 0.6, somewhere around there? Okay, what we did here is we squared 3.44, we subtract it to the other side, okay, which would give us negative 11.83. Then we divide that by the negative 19.6. Okay, divide that 19.6 over, don't add that over. Okay. Last question, how far will it travel horizontally? Okay, which means we're solving for what variable? X final. Okay, we don't have very many horizontal equations, right? They're super abbreviated. When we use this equation, x final equals vxi times time, right? What time are we going to use? The time to peak height or the whole time? The total time. Make sure that you're very, very careful there, okay? So to find x final, we would take 5.51 times 0.70. Okay. Can somebody tell me what the difference is in this problem and as compared to the ones we've been doing? Yeah.
It starts at 12 meters.
It starts at an initial height of 12 meters. Okay, so what does that mean about our final height? Is it gonna land above where it started or below where it started?
Below.
It's gonna land below where it started. So that's gonna make our y final not 0, right? And that's gonna make our problem not symmetric, which means we eliminate the shortcut possibility here. Right? We can't use that shortcut method. Okay, so go ahead and get written down what you need to. I'll kind of draw you a diagram so we see what's going on here. Remember that this little initial velocity triangle that we're making is extremely magnified, right? It's only moving with those particular components for kind of an instant, right? The instant that it leaves and becomes a free-falling object, it moves with those components. But that, when we draw that triangle, it's really, really magnifying that instant. Okay, so just understand that. It doesn't really travel in a straight line like that for very long. It's really, really instantaneously, but we're blowing it up so that we can see it correctly. Okay? All right, let's go ahead and start solving our components then. Okay, from there, what other variables do we know? All right, we're done with the 89. We're not going to use that anywhere. We're done with the 31 degrees. Okay, 12 meters. Is that going to be our y initial or our y final? Okay, you can do it either way. What do I like to do, right? Since I draw my origin here, I like to make my y initial equal to 0, and that would make my y final equal to negative 12. Okay, that would be, again, after it completes its peak height and goes to the ground. Okay, these equations do a lot of the extra work for you. Okay, so don't overthink this kind of stuff. Okay, but let's look at our. We already solved our first question, right? Here's our two components. How long until the cannonball hits the ground? Okay, so that means we want to solve for total time, right? Can we use the shortcut method here?
No.
No, we cannot. It's not symmetric. They don't start and end at the same height. Okay, so what equation do we probably need to use to solve for time?
Quadratic.
Yeah, the quadratic one, which would be the second vertical equation, right? Y final equals Y initial. That's the equation that we're going to use most of the time when we want to solve for time. Okay? So my y final is negative 12 because it's landing 12 meters below where it started. Okay, is everyone clear on that part? Give me like a head nod if yes, that makes sense. Okay, it's landing 12 meters below where it started. Initial height was 0. Initial vertical velocity is 45.8 times time plus 1/2 negative 9.8 t squared. Okay, so let's get our quadratic set up correctly with our a, b, and c terms. When we set up our terms, what do they need to be equal to? 0. So right now we have everything set equal to negative 12. That's not going to work. So we need to add 12 to the other side. Okay? Does that make sense to everybody? We have to set our quadratic equation equal to 0. And right now it was set equal to negative 12. We want to add 12 to the other side so that now our c term becomes positive 12. So we say 0 equals negative 4.9 t squared plus 45.8 t plus 12. Okay, so our terms are A, B, and C. Okay, so this is already after the square root? I don't think so. Oh, you did square root. It's square root. See, there's b squared minus 4ac, which is fine. Square root that. Square root that number. There we go, that's better. That's better. Okay. So then we want the numerator to be negative or positive. Well, we want the total number to be positive, right? If our denominator is negative, we want our numerator to also be negative. Okay, so that way you probably only have to do one of them. Okay. Okay, what do we get for our final distance here? 732.48, somewhere around there. That's a long way.